Welcome back. In Part 3, we explored embedded thunderstorms, frontal cloud systems, and how to read charts to spot hidden dangers. In this final episode on clouds and precipitation, we'll cover frontal clouds, visibility impacts, and strategies for navigating complex skies. Let's start with frontal clouds. When two air masses meet, the warmer one rises over the cooler one, creating clouds and often precipitation. The type of front determines the cloud structure and flight conditions. Warm fronts produce wide layers of cloud. You'll see high cirrus first, then altostratus, and eventually nimbostratus with steady rain. These layers stretch hundreds of miles ahead of the surface front. Flying through a warm front means long periods of instrument conditions, light to moderate precipitation, and low ceilings. It's rarely turbulent, but visibility is poor, and icing risk is high in layered clouds. Cold fronts, on the other hand, push under warm air aggressively. They produce narrower cloud bands, but with more vertical development. Expect cumulus, towering cumulus, and often cumulonimbus. Cold front passages bring gusty winds, showery precipitation, and possible thunderstorms. The ride may be rough, but visibility clears up quickly behind the front once the air mass stabilizes. Occluded fronts mix both characteristics. Warm air gets lifted above both cold and cool air. These fronts generate widespread cloud cover, often including embedded CBS. They're common in complex low-pressure systems. Now let's discuss visibility. Precipitation affects visibility both in the air and on the ground. Rain reduces forward visibility. Snow reflects light and creates whiteout conditions. Fog and drizzle obscure runway markings and terrain. Mist or haze from pollution also lowers contrast during descent. In IMC, pilots rely on instruments to maintain attitude, heading, and glide slope. But the transition from instruments to visual near minimums can be tricky if precipitation or fog hides runway features. Let's review approach categories. Category I requires 200-foot decision height and 550 m RVR. Category 2 goes down to 100 feet and 300 m RVR. Category 3 allows landings with no decision height and as little as 75 m RVR. Flying in rain with RVR near minimums requires precision flying, autopilot use, and full briefing of missed approach procedures. Even then, if the runway isn't in sight at minima, go around. Now let's talk precipitation and lighting. Heavy rain or snow reflects light, making approach lights hard to see. Combine that with fog or a dark night, and depth perception suffers. Brief crews for possible late runway acquisition. Always monitor RVR reports, tower visual range, and pilot reports. If other crews report runway in sight late, plan accordingly. Add a margin if needed, especially when flying to unfamiliar airports. Alternate airports are even more important in these conditions. When widespread frontal systems reduce visibility across large areas, your alternate might be facing the same low ceilings and precipitation. Use forecast trends to pick the best alternate. Check TAFs for improvement or deterioration. Ceiling and vis forecasts. Fuel burn calculations with extra holding timed on T get caught in a trap where the destination and alternate both go below minimums. Let's explore deviation strategies. On en route charts or GPS displays, use weather overlays to see precipitation zones. If a frontal line is ahead, request vectors or lateral deviation. 5 to 20 miles is often enough to avoid embedded cells. If embedded CBS are suspected, avoid crossing frontal boundaries at the worst times, like late afternoon or during maximum heating. Instead, climb above stratiform layers early, or delay descent until reaching clearer air. Also watch for frontal turbulence, especially near jet streams. Strong wind shear and unstable layers can create moderate to severe turbulence along frontal boundaries, even without visible clouds. Let's break down a sample case: URI flying through a warm front at FL 090, with light rain and +1 degree Celsius. The stratiform layer extends up to FL 120. Temp and moisture equals icing risk. Expect a slow ride and monitor airframe icing closely. Another case, URI descending through a cold front with building cumulus and occasional showers. Wind is shifting fast, and ATC reports moderate turbulence. Reduce speed below turbulence penetration speed and brief for go-around. Let's talk about weather decision-making in these scenarios. Ask yourself, can I maintain alternate options throughout the route? Are arrival airports getting better or worse? What are the escape routes for climb, turn, or holding? How is visibility trending at destination and alternate? Also factor in your aircraft's capabilities. Not all aircraft have anti-ice, radar, or terrain mapping. Know your equipment limits and when to say no to continuing in poor weather. Let's recap useful cloud and precip terms on METARs and TAFs. BR equals mist. FG equals fog. RA equals rain. SN equals snow. TSRA equals thunderstorm plus rain. DZ equals drizzle. FZRA equals freezing rain. SHRA equals rain showers and plus or, before the code means heavy or light intensity. Recognize these codes quickly, and you'll build better mental models. Combine with cloud cover info, BKN, OVC, and ceiling data to assess approach viability. Finally, let's cover mental strategies. Stay flexible. Weather changes fast. Stay informed. Layer your data, METARs, radar, satellite, PIREPs. Stay sharp. Brief for go-arounds and alternate action before descent. Stay ahead. Make decisions before reaching a critical point. Don't wait. Let's wrap it all up. Clouds and precipitation aren't just visual cues, they're dynamic systems that affect every aspect of flight. Knowing how to identify, interpret, and respond to them makes you a safer, smarter pilot. In the next episode, we'll launch into a new series, Thunderstorms. We'll break down how they form, what they do, and how to navigate around them with precision. See you in Meteorology number 31, Thunderstorms, Part 1.